Welcome to Brain Vision.
Hey everyone, this is question number 44 from chapter 14. In this problem, we're given a copper pot of mass 0.5 kilograms. It contains 0.17 kilograms of water. Both of them are at 20 degrees Celsius. And then an iron block of mass 0.25 kilograms is dropped into the pot, and it is at 85 degrees Celsius. So then we're asked to find, that's all of our givens, and we're asked to find the final temperature of the system, and we're told there's no heat loss. So again, we're having temperature changes, masses, so we should recognize Q equals mc delta T as our go-to equation for this kind of question. And we're solving for final temperature, but we need to go ahead and define Q for each one of the parts of the system, which would be the copper pot, the water inside the pot, and the iron block. So Q for the copper pot, let me draw a better Q. QC for copper pot is equal to mass 0.5 kilograms. C for copper is 390 joules per kilogram K. And then for delta T, we know that any change is defined as final minus initial. So we're going to see T is our final and minus our initial for the pot is 20 degrees C. Okay, so that's our equation for QC. Now we can go on to Q of the water inside the pot is equal to mass of the water, 0.17 kilograms. For water, C is 4190 joules per kilogram K. And then our delta T, again, is going to be, for the water, it starts at 20. So our final is T, we don't know that, minus 20 degrees Celsius, which is our initial. And then we can do Q of the block, which is equal to mass of the block, 0.25 kilograms. C for iron is 470. And then our temperature is going to be our final T minus 85 degrees C. So the same thing for every single one of them. Okay, so we have these three expressions. Now we can go ahead and multiply them out and simplify them, and we're told there's no heat transfers, so all of these are going to add sum equal to 0. So the sum of Q is equal to 0 is equal to, so I'm just going to simplify and add these. So we multiply the first two and then distribute to the T and the minus 20 degrees C. And that's going to give us 195 joules per Kelvin times T minus 3,900, excuse me. And then we do plus water, you do the same thing, multiply the first two and then distribute to the T and the minus 20, plus 712.3 joules per Kelvin, T minus 9,988 joules. And now we go on, I don't have space, I'm going to go to the next page and rewrite the first part of this. So the sum of Q is equal to 0. So we had is equal to 195 joules per K times T minus 3,900 joules, and then plus 712.3 joules per K minus 1.425 times 10 to the 4th joules. And then our final one for the block is plus 117.5 joules per K minus 9,988 joules. Looks like I flipped those around. So this is our final expression. So now we simplify and we can solve for T. Combine like terms, combine all the T's, combine all the whole numbers. You end up with T equals 2.814 times 10 to the 4th joules divided by 1025 joules per K. And that gives us a final temperature of 27.5 degrees Celsius. So as expected, the block cools off and the water temperature and pot temperature increase, and then they reach an equilibrium temperature at 27.5 degrees Celsius.